Very good evening to you all. Welcome back to another session on AI in lab medicine. This session is a part of our ongoing course on AI in lab medicine. So far, we have finished the basics of AI itself, and after that, we covered some of the information about AI in pathology and hematology. During those sessions, we got to know about how we can build our own AI models, be it machine learning or deep learning, and also some day-to-day use case apps using AI. But some of the participants had asked me that if there are any ready-to-use solutions for AI in pathology. I know quite a few solutions or the startups, some of which are international. But today I wanted to showcase you or introduce you to one of the Indian startup that is doing very nice work in the field of AI and pathology. That's why I contacted Dr. Devansh from Turocrates if we can organize a webinar showcasing what Turocrates has for pathology AI enthusiasts. Thanks to him and Mr. Swapnil, the CEO of Turocrates.ai, for accepting my request and becoming a speaker for today's session. So without wasting any more time, I would like to invite Mr. Swapnil, CEO of Turocrates.ai, to deliver his talk and let us know what he has to showcase us in terms of how we can leverage Turocrates.ai for pathology. Over to you, Mr. Swapnil.
Thank you, Dr. Atul, for the introduction. Hi, good evening, everyone. Uh, Glad to be talking about on a Sunday evening. Yeah, so I'll be quickly going through. Let me just share my screen first. Just a couple of slides, like 7 to 8 slides in total. And I'll be talking about who we are, what we are building, why is it important, how is it different, really different from what is being done in the US, EU, or any of the developed markets, and why that approach may not exactly work for us, and how you can be part of, I'll say, modernizing pathology and part of the new digital pathology and AI drive. Right. And post that, I would love to, get on a Q&A and talk about if any of one of you has any questions, and we can make it more interactive. All right. Yeah. So the name of my company is Turocrates, and we have been in operation for around an year now, and we are focused on the digital pathology and diagnostic space. So one of the reasons for this was, so my co-founder Devansh, he attended a webinar at TMH, and where they were talking about pathology being one of the last frontiers of diagnostics. Like radiology has been digitized, a lot of companies are building AI algorithms for radiology, but what has been happening in the field of pathology? Why is it lagging behind? So that is what gave us an idea, and that's how we started our journey. And now we are fully focused on building in the space, building the digital infrastructure, building the AI algorithms, and integrating this into the workflows of labs so that you people can use these technologies in your day-to-day work. All right, so I'll keep it short. Post that we can have any kind of questions. I can answer any kind of questions that you might have. Yeah, so who we are just a small team of engineers and doctors. So this is my core team, and this all has been possible because of them only. So there's Molek, who's a soft CTO. There's Devansh, who is our physician turned AI scientist. There's Dr. Sanjay Arora, who is the ex-CEO of Suburban Diagnostics, and Dr. Kshitij. And also thanks to all my collaborators from various centers who we have worked with so far, who have helped us build these AI models, helped us validate it, helped us in the deployment process. Yeah, so the reason we are building is we have identified a lot of shortcomings in the domain. So a couple of them being one of the biggest challenges is that there's a dearth of pathologists. There's a massive shortage of pathologists. So I myself come from a tier 2 city. And if, let's say, I have to carry my own biopsy sample and go to, I'll say the nearest hospital to me is AIMS Delhi. So from Jammu, I have to travel all the way to AIMS Delhi and get the answers to my whatever uh, tissue solved there. Uh, so the thing is, there's a massive dearth of pathologists and even WHO recommends that the ratio should be 1:10,000, but in India it's 1:100,000. And with the increasing cancer incidence in India, the same workforce will be short-staffed. They won't be able to handle so many cases. Another major problem is, like, this is something I've seen with my own eyes. Different pathologists having different interpretations for the same slide. And there are well documented cases for this, be it KI counting or Gleason score, Gleason grading, or even the unavailability of a particular subspecialty pathologist in that region. And then these slides or blocks have to travel across the country, reach and get diagnosed by the appropriate person because the relevant pathologist is not available in that area. And another thing is that I still feel that we have not yet explored the full potential of a tissue slide. So there's a lot of developments being done in the fields of spatial biology, let's say, where you can understand the tumor microenvironment from a simple H&E glass slide. So there is still a lot of potential that can be found under a glass slide while you look at it through your microscope. And all of this is possible. It's possible to address all of this if we have some kind of infrastructure built in, if we have, let's say, a digital technology or AI introduced into the systems. So there's a lot of development happening in the West. There are these foundation models coming out of these big research labs in US. And these are like very good models. Foundation models like Conch, Uni have been trained on millions of whole slide images from US, EU hospitals. And there are a lot of disease specific models as well, which are coming out of these US based companies and startups. But the thing is, they are well embedded into the Western ecosystem. And a major thing is they require a scanner to which is the basic, a whole slide image is the most basic thing which is required for running these algorithms. Hence, a scanner is required. But in India, most of our centers can't afford a scanner. One of the biggest reasons is the cost of the scanner, and the second is there's no direct return on investment which labs find out of the scanner because you have to pay for a recurring storage cost every time you digitize or store it in a cloud storage. So what can we do? Are there any solutions which are tailor-made for LMIC settings? Let's say, is there a way I can use my microscope itself? Turns out there is. So a major chunk of our research since our inception has been focused on approaches utilizing a microscope. How do we utilize a microscope to run AI algorithms? So there are all these fancy smartphone adapters you can find. You can attach your phone camera to the binocular port of the microscope, and it will be able to it will allow you to see the digital feed. So is there a way I can hook that up to my PC, get that live feed, run an algorithm on it, put that result into a report, let's say sync it back to the LIS system, and the report gets finalized? Or is there a way, like right now there are all these trinocular microscopes wherein they can generate a live feed, but they are still I'll say in silos. You have a trinocular port microscope which will generate a live feed, and that's it. Can you run an AI algorithm on it? Can you integrate it with your LIS system? Can you do synoptic reporting on it? Currently, the answer is no. But I think this is what we need to solve to bring India or these LMIC settings into the digital world. Because the hardware already exists, the resources are less. It's just the software which is needed to give that extra push. And we have developed a couple of algorithms which do work on a live slide. You just require a smartphone or a trinocular port in your microscope and generate the live feed and run these algorithms. So what we have built is effectively two systems. One is for labs, we call it Turopath, and the second is an education and research tool, call it TuroEducate. So Turopath is just an attachment to your existing LIS. You can use any LIS that you want. But your LIS won't help you to digitize a slide, run any algorithms on it, do telepathology, anything like that. But with our system, all the cases can get automatically sent from any LIS to the system, and you can do the reporting, diagnosis in it. So a couple of salient features that we have are, we have a lot of synoptic reporting templates built. You can generate your own as well, actually. So which will help you to report. We can integrate with the whole slide image scanner. We can integrate directly with the microscope itself. So you can generate the live feed and perform the reporting. Even run your AI algorithms on it or build your own AI algorithms. And once the slides are digitized, you can even send these slides to different parts of the country to get second opinions. The second platform is our educational platform, which we are utilizing as a digital slide library. So I am aware that there are systems and companies in the US who have uh, deployed their platforms in the country, but the pricing doesn't work for the Indian market. So both of these systems are made by an Indian company, are developed for the Indian market for you guys. So you can store the slides digitally and take them for conferences, CMEs. You can perform a lot of smart annotations on it, have collaboration projects. You can view these slides offline, present them, in a low internet setting as well. And one of the major use cases is biobanking. By biobanking, I mean when a lot of data starts accumulating, search becomes very, very difficult. So we have all the AI algorithms. So when we talk about AI algorithms, it's not just limited to diagnosis. AI algorithms are also used to make the data searchable here. So we take out the metadata tags, we take out the interpretation from images, from data, and allow you to search based on natural language so that you can get the data faster. You can fetch the data faster. Yeah, so I think I had shared on the group link for our educational system. And I just wanted to show that live demo here. So what can an AI algorithm do on a pathology side? Actually, it can do a lot. So let me just share that here. I think you can also open it at your own end and try it. So there are namely three types of tasks, I'll say, which AI algorithms can be used to perform on a glass slide. First one is a screening task. So there's a massive whole slide image. Let me say that I need to find a tumor region, or I need to get into a particular region. I need to just sign off on a report whether this contains a tumor region or not. If it contains, give me the region of interest, give me the tumor volume, all of that. Second type of algorithms would be quantification algorithms. Let's say mitotic count, KI, Gleason, any of these would be covered in this. And the third class of algorithms are the more advanced ones, which are prediction algorithms. Let's say prediction of MSI status from an HNE, IDH1 mutation from an HNE, and other such advanced algorithms. So let me just open it here. Yep. So this is the region of interest detection algorithm. Here we can detect micromets in the lymph node. So let me just run it here. So this gives me a heat map of the affected regions, and I can see, let me just toggle it. You can see the contrast here, and it's showing the result here with the interpretability. So all our algorithms are built to be explainable. It shouldn't be like a black box to you. So it will give you the regions of interest. It will give you the largest focus, the tumor area for each of the slides. We go to another one. Here I'll run the model. Yep. So at a low magnification level, I can find this region, and here I can see the regions of interest. Go to another one. Let's say the Gleason grading. So just a disclaimer, both of these models, what I showed you, these have been validated on real patient data. These are not just research tools. So we have validated this across multiple institutes as well. So some of our algorithms have passed on that validation. We also have licenses for a couple of our algorithms, but some of our algorithms are still in the research phase. Yeah, so it will give you the Gleason score here, along with the region of interest. I'll show you for someone else. Yeah, you can just play around with it. It's the score. So one way to speed up the development process is to find an appropriate foundation model. So we, let's say, figure out a good open source data set. We figure out a ideal architecture that we can use. We extract the features from this image, from a whole slide image or a tissue patch. And then we build a classification layer, a segmentation layer, or a detection layer on top of it. Once that is done, then we can go and ingest real world data, let's say data from TMH, AIMS, or any other centers. And we fine tune our model on that. By this methodology, we require lesser amount of data to make the model perfect for that particular location. So to make it generalizable, we need to ingest a multi-center data, like the data should come from different patients of different regions, multi-scanner data, different stain variability. So there are a lot of techniques that are used to, I'll say, normalize the results. Because I can't keep on ingesting data from 100 or 1000 institutes and still for the next institute it fails. So we have to employ a more generalized method so that after a certain point, the model, the metrics plateau or they reach their desired accuracies. So on the LMIC note, we recently built out this model and we presented this at the European Congress of Digital Pathology as well. So our MSI model, which can predict the MSI status in colorectal cancer from an H&E slide, is built on patches. So imagine that this particular patch is visible from your microscope. So you are able to digitize the live stream, and this is a patch that you are seeing. So it requires a human in the loop. Once you have the tumor region, you can run the model and the model will give you a result. And for this, you don't even need a scanner. You don't need to scan this entire slide. So a lot of models can work on a patch basis, but they would require someone to guide them. But the results are, I'll say, fairly similar, whether it's done on a whole slide image or done on a patch. Yeah, there are a bunch of models. You're free to explore this. We have just made it for maybe not in this. I'm not able to see anything. Yep. So one particular thing here is attention. So attention is basically a technical term we would use in the process of model building. It basically will give me a heat map. It will basically tell me the model is interested in these regions. It's highlighting these regions more times than the other regions. So just a considerability, just explainability source for you when the model has given its results. So what we could do is we can backtrack. So a pathologist from a H&E slide, there are a lot of morphological features which a AI model can catch, which a pathologist, a naked eye, won't, unless they have a lot of experience. But we can't have, experience like highly trained, experienced pathologists everywhere, right? So we would need some kind of co-pilot, someone to assist us. The AI plays that role in that case, and we can learn from this interpretation and use it to train ourselves. Like what kind of morphological features has this algorithm caught? Maybe we can backtrack and use it to self-learn. So AI learns from the humans and humans can learn from the AI if it's explainable enough. All right. Yep. So these are just a couple of use cases, and there are a lot of algorithms being developed in different parts of the world. The difference being the way you need to use them. It could be a scanner modality, it could be a microscope modality, and both are possible. Using just a simple microscope as well, you can do a lot of these, run a lot of these algorithms. So I think one of the questions was around this line. So I'll just address this here. So where do you come in? By you, I mean, let's say the domain experts. So if you are a student, resident, researcher, you can utilize a platform like Turocrates. It's free to explore. You can use it to host your slides. You can do your research through it. So it's, I'll say, built as an enhanced version of QPath, because sharing of slides is one of the most painful things in model building, and like apart from annotation. So if you are annotating a slide on a desktop based system, there's a lot of back and forth that you have to do with the institute. Let's say I'll build a model, I'll draw the annotations, and I'll have to send it, upload it on Google Drive, then they will download it, and the process is a long back and forth. So a cloud-based system basically eliminates all of that. So you can annotate, you can add multiple people in the projects here. So like it's just like you can explore it here. The same platform can be used for annotations as well. Second. So that's one thing. And also annotation in itself is a very big use case. So all the AI algorithms that we develop, we are like, I'm a trained engineer, let's say. I know how to build AI algorithms, but I need someone to tell me which regions to look at, which regions should the AI mark, or this is right or this is wrong, how to make the analysis better. So that's where the domain experts come in, and they can help us annotate the cases. And we do extensive research in this field. Like we have just been in 1 year in operation, but we have published uh, a great deal of papers, and this is going to be an ongoing trend. But the idea is not just to do research. Any algorithm, let's say you help us annotate, we do the research together. But post that, the goal would be to how do we make this algorithm deployable in your setting? How do you use it in your daily world? And I told you there's a microscope-based modality as well. So that's how we could try to do it. And if any of you is running a lab or part of one, a platform like Turocrates, which will just seamlessly integrate with the LIS system and let you do uh, any kind of digital based reporting or running your AI algorithms. It will make it all seamless without even touching, like nothing gets replaced. You can integrate a microscope, integrate your LIS into the Turocrates system, and it will start working out. Yeah, so this is my last slide here. So it's just some generic things that AI and pathology is already here. Uh, we all know how fast the field is progressing, and pathologists are going to define how these models get built, how this field is going to get shaped, and that's what we need your expertise on. Yeah, with this, I conclude my presentation, and I think I'll open it up for any questions. In any like maybe I missed a lot of things. Like I'm open to any questions.
So, Swapnil, there is one question specifically that is asking about, is there any AI model being developed for bone marrow biopsy cells?
There is, yes. Yeah, so I think there are a couple of questions in the chat. Uh, was did you get an app? Yeah, it's like a web-based software. I have shared the link on the group. You can log in using your Google account, and you are in. So a couple of parts to this is one is a platform library. It's a free, like we have collected these slides from across the country with proper annotations, proper clinical history, proper clinical documentation. You can view the slides, and that's one part. Second is that it is your own tool. It can be used as your own personal Google Drive, as your own personal whole slide image repository. So one thing I think which I missed is that we have been able to create a compression algorithm which can reduce the size of these images by more than 70% without any kind of diagnostic quality loss. And we have a patent for this as well. So all of the images that we are storing that in a compressed format. So any of these images, and we have validated this extensively across with multiple metrics like visual, I'll say morphometric, how the cells are different in in a compressed image versus the original image, and even a AI-based analysis. We have ran AI algorithms on a compressed image versus a normal image, and there is there's no measurable difference. So that's an advantage, and we can store massive slides at a scale easily because of our tech. All right. Yeah. Um,
So, Swapnil, I'm just
Yes.
helping you out. There was one question in the beginning only that was asking about the pricing of the software and training sessions. I think you can briefly mention about it, and the pricing details can be directly discussed with you outside of the meeting. They already have your contact number as well as LinkedIn information, or you can post it again in the group.
Yeah, sure. That's something we can do. One thing I'll maybe like to highlight is learning about algorithms is great. How they get built is also fine. But what now, like this, an initiative that we want to start, which is a more decentralized form of training and development. So let's say we'll go deep into one algorithm that we have built. Let's say the MSI algorithm from which will detect the status from HG slides. So this is so on this particular algorithm, we can have data collected from multiple sources. Like it's going to be your data itself, and you can annotate it. We can train the model and deploy it in your own labs because this model will work on a microscope based approach as well. So this is something we want to do model by model, break it down, and make it more up in like applied AI. I'll say.
So, Swapnil, this is Dr. Malika.
Yeah. Hi, Dr. Malik.
Hi. So, you have validated in histopathology only, or it's on IHC also, like ERPR, HER2/neu, or PDL1?
Yes, so we these are part of the IHC quantification algorithms. I'll show you in the quantification section here. We have IHC quantification, and we have a license for this particular model. So if I run this KI algorithm here, so it will give me the positives. It will give me all the scoring, and then I can see the positive cells, the negative cells, all of that. So this is done for KI67 and ERPR so far.
Okay.
So there are two steps to this. One is it will detect the tumor region in all of these slides first, and then it will give the scoring. So this is a whole set image based approach. The second approach would be if you directly go into a tumor region and run it, then it will know what the particular tumor regions are in that region of interest. It will directly give you the scoring. So with a microscope as well, that this is possible.
So, does it differentiates between the invasive and the ductal carcinoma in situ IHC
Yes,
patterns?
it does.
And in PDL, what are your validations like, and what all like PPS scoring, CPS scoring?
For PDL1, we are still gathering data. We have trained
Okay.
model like on the open source data sets, but that's still under development. I'll say we don't have a very conclusive modeling for PDL1 quantification yet.
Okay. So I would be interested if you would like to have a like PDL1 validations. You have a lot of experience. So
All right,
working in a high volume lab. So we can just talk it separately.
our doctor.
Uh,
Right.
so, Swapnil, there are 5 or 6 questions in the chat box that were
Mm-hmm.
dropped in last couple of minutes. Can you quickly go through those also?
Right. Yeah. So images you upload on the app are your property. They won't be used to train the AI models unless explicit permission is given by you. Patch level regarding the patch level thing, do you need any question? Yeah,
So
so
one
yeah, please.
there is one question. So will it take it into account all the artifacts like staining artifacts, bubble artifacts, and all other like sometimes there is a we have to focus the field in a different ways to get the cells focused. So all these things will be taken into account by this software.
Yes. It's here. This is a quality control algorithm that we have made.
Okay.
It will detect artifacts like tissue fold, dark spots, pen marks, out of focus. So yes, during the training, uh, quality control model is the first to run. It will clean those uh, images and like basically tell the algorithm if these are fit to be trained or like, are these even trainable or not. And based on that, it will like for the images which do meet those certain thresholds, it will go ahead and train the model.
Because sometimes the tissue is very poorly preserved, and
Right.
we really need an expert eyes to look through it. So how good is your software in that?
So actually, we have benchmarked this against global players, and it performs like in some cases even outperforms them. We're happy to share this model with you, and you can utilize this in our setting, and we'll test it out.
Sure, sure.
All right, heat maps is basically it's the model's internal way of telling which regions are of interest or not. So it's if like some of you are familiar with how deep learning works, is that I'll okay, fine. So it's multiple, let's say neurons are there, and there's a the image features and everything passes through all these neurons. I get a result, and then I'll understand which of these neurons, which of these features contributed the most to the result. And based on that, I'll start highlighting those features. So a heat map is just a color map to highlight the result when it came out from a particular for a particular task, which of the regions contributed the most. And in some cases, it can be used to explain the actual way a model is working. In many cases, actually, it's in the MSI case, it will tell you the exact morphometric feature, the morphological features, which are uh, helpful to predict that status from HE side. WSI is not necessary for building a model. So like I said, one of these algorithms has been developed at with validated at AIMS Delhi, and it used tissue patches. So a 20x or a 40x uh, image was taken. We out of from that screenshots were taken out, and we had the ground truth, and based on that, the model was trained. The only challenge with such an approach is you will have to be in the loop. You will have to point it to a tumor region, or the region of interest has to be small, because once you like start looking at a tissue side, you start with a very low magnification, 1x or 4x, let's say. At that level, well, it can detect the tumor regions correctly, but to make it more enhanced, you have to go to a higher magnification level. Let's say at 20x, it will be able to correctly discern the tumor boundaries and then run the algorithm. But at a very low magnification, it will be difficult to figure out the tumor regions itself. So that's why you will like a pathologist or a domain expert has to be in the loop and guide it to the exact regions. And then yes, a patch-based algorithm would work. On a DB600, yeah, it's possible. All right,
Hi,
delete. Oh,
Swapnil.
okay. Yes.
Going back to your patch to patch question, what is the variability between patch to patch? Have you checked on a single slide? What's the variation between patch to patch for the MSI status?
Yes, we have checked that. So when I say patch to patch for a particular whole slide image, if I have to train a model, we do take out all these patches from the tumor region. And in the tumor region, depending on the algorithm, let's say for the MSI algorithm, there is very less variability in the values. So if I have to tell in terms of course, like a similarity score, it's around
Uh-huh.
0.992 or something, which is a similarity between the results.
Got it. Thank you.
So that's why to make it robust, either we have to train it a lot on a lot of patches from different regions of the tumor, or we have to, while running the like in a lab, we have to do the test on a multiple patches to give the final answer, which can be difficult. So during the training itself, we have to make sure to take different kinds of patches from the the tumor region.
Yeah, that's what I thought, because just taking it to the patch level, it is, and taking that to the clinical level data, like, or clinical workflow is kind of, I would not say risky, but I'm not sure how much would be the concordance between the real life IHC or PCR and to the outputs.
Right.
Yeah.
Right.
So these
Yes.
one more question. So these
Yeah.
patches, this pathologist is going to annotate these regions, or it's like how it is how it is working?
So for patches, yes, the pathologist is going to annotate this. So let's say this was taken at, I said, let's say 20x, or there are a lot of 40x patches also that we have. So we have a final ground truth. I think one of the questions was also about this. For the MSI algorithm, yes, if I have to train a model, I need to know the results of the molecular test. For, let's say, this particular patch came from a particular tissue slide, and I beforehand knew that from the molecular test that the result is MSI high. So my input to the model will be image patches from that particular tissue and MSI high as a result. So yes, a molecular test is required for basically that serves as the ground truth. Without that, training a model is not possible at all. So yeah.
Also, when you are doing these patches, are these patches coming from WSI, or you are saying it, you are going to take it to the microscope level and somebody can capture picture from the microscope? So how
Yes,
do
ma'am.
we even control that? Because different microscopes have, like, or the microscope cameras for that sake have like a different capture modes and image formats and variability at different levels. So how do
Mhm.
you control that, or have you taken that in consideration?
Yes. So the image you see in front of you, and even the model was trained on a mostly microscopic images, mostly. So these images were captured using a camera either from a smartphone, which was attached in the, like in a cam, like on the binocular port, and the
Mhm.
pics were taken from that. And we also ingested data from full side images. So let's say a particular scanner was available, image patches were taken by doing screenshots from the WSI, by running a particular script to extract the patches from the WSI, and even capturing it using a mobile phone on the microscope. So based on all of this, like I mentioned, there are differences in the resolution. There are differences in the staining quality. So
Exactly.
so yes, so for that we need to take into account. We need to build out these normalization techniques, because I can't train on infinite data. There's not a lot of data to train on. So I have to
Mhm.
figure out some smart techniques, basically. That if I have images of multiple resolution, but it's the same tissue, how do I, make these results consistent with each other? So that's how we figure. We know the resolution from a microscope. Let's say we know the whole slide image resolution, and based on that, we build out these normalization techniques, so that next time it sees another data point, next time we ingest a patch, it understands that I have to, maybe subtract something, or add a bias, add a variance, add something, or subtract something from it to make the results consistent. So yes,
Makes
ma'am, this
sense.
all is taken into account.
Got it. And you said these features are interpretable, right? So
Yes.
when it goes into algorithm, do you explain to pathologists what is the explainability between these, for example, MSI result, so that they are confident into the result, or it is like a behind the screen, or it's a pet your, like, intellectual
Yes,
property?
we do that. No, we do that. Explainability is something that I think should be there in all models.
Mhm.
Otherwise, why will you trust, right? You
Right.
have to use it in a daily practice, and it's very, in some cases, let's say down the line, it becomes uh, super accurate. Maybe we can think of this. And
Mhm.
another thing I want to mention here, while we are on the MSI subject, I will not make a statement. So to say this is a predictive algorithm, right? I am predicting something from an H&E. So I'll not say I'm replacing IHC, or I'm replacing molecular test. No, till the models achieve a good sense of accuracy, a good metrics, I'll just say I'm reducing the dependence. I'm maximizing for negative predictive value. I'll just tell that, okay, this particular patient does not need to go for like they don't have the MSI mutation. So I'll rule out patients, screen them off so that I can reduce the dependence on genetic testing.
Makes
Because
sense. Yeah.
for many of these cases, we have a lot of skew in the data, right? 80-20%. 80% of the population won't have this like MSI high.
Mhm.
So, and a lot of data is available for the negative, like MSI low. And even my training starts to have problems. So one important point is for a lot of biomarkers, positive data is very, very less. For IDH1, I think someone had asked the question, we face a similar problem. The positive data is less. For MSI, the same case. So it's just like I'm trying, like there are artificial ways, there are methods to increase or augment the data, and we do employ those. But at the end of the day, I'll just make these a bit good, better screening tool for the next couple of years. I'll just try to reduce dependence on IHCs and genetic tests through my
Yeah.
models.
Make a lot of sense. Thank you.
Yeah, not a question actually. It's more of a comment. But also here, Swapnil, maybe you remember me. We had a discussion, I think, last year.
Yes, sir.
So it's great to see the model and software has evolved so much, and it's much more robust and with much more algorithms nowadays. So yeah, great work. Congratulations to you and your team. Great.
Thanks, sir. Any other questions?
There is one question that is about compatibility with immunofluorescence images. Can you check it out? It's by Dr. Nichols.
Right. No, we have not built any model which would be currently like it's the immunofluorescence images are not under our AI model development purview. Basically, the data ingested is normal like HE, IHC images. It's this particular category is something that we have not touched yet.
So I think all of the questions that were asked in this Google Meet chat have been answered by you very well. Also, the questions which were there in Google form as well, you have covered during the session also. So if there is any other question, feel free to unmute yourself and directly ask. Otherwise, we can end this session.
I think last question, are there any of these algorithms currently being used in the clinical workflow, and which are those?
Yes, ma'am. So the places where we have developed these algorithms, we are utilizing like those centers are utilizing these algorithms. Let's say the quantification algorithm, which are the one is the retic count, the mitotic detection, and the IHC quantification are being utilized in the clinical work. And something like Gleason's grading is also something we plan to deploy in the next couple of weeks, again for regular work. But they have been already validated, but deployment is something which is pending for this particular algorithm. Apart from that, IDH mutation algorithm, the prediction algorithm is also being deployed in the clinical setting right now.
And going for those molecular algorithms, do you have like a requirement how, like especially cholangiocarcinomas and things like that, we usually have a limited amount of tissue. So have you faced any challenges in that area? Like how much tissue do you need in order to have a good call?
Yes, ma'am. So we are currently in the process of augmenting our data. Okay, what you mentioned. So many of these have like most of this is like based for cholangiocarcinoma itself. I think it was a question the quantity of the tissue. Is that
That's right.
correct?
That's correct. Yes.
All right. One second. Devansh, are you in the call here? Hello.
If it's not available, that's okay.
One second.
Sorry, I was just unmuting myself. So, ma'am, basically, it's not like for molecular testing, you need some amount of tissue, right? So, actually, these predictive algorithms are mostly most useful in the QNS cases where there's no enough quantity. So, the amount of tissue, as long as you can make one slide, is more than enough. It's not like the molecular testing. So that is what I think you were asking that only, right, ma'am?
Yeah. I just wanted to know, like, what's the detection limit basically? Like, how
As
much do
long
you
as you have
need?
one good slide, that's more than enough.
One good slide. Okay, sounds good.
Yeah.
Thank you.
During training, you would require to have diverse data, but like Devansh mentioning, inference can work, or like results could be on a small tissue sample as well, as long as one set can be created. That's true for actually every algorithm.
Sounds good. Thank you.
Something about bone marrow. Yes, the algorithms are compatible with bone marrow biopsy, Dr. says. Yes, so we have a CDSU license for our quantification algorithm, the HC1. Most of these algorithms have to have a class C license, and post that they can be used in clinical settings. But that being said, if someone can utilize these algorithms for their internal purposes and just like acting as a co-pilot, but it's the ultimate decision has to be taken by the pathologists themselves. So pricing is all right. So it's two different systems, right? For the education platform, since this is meant for individual use, like you, me, anyone, this is my personal account, let's say. So any one of you, us could have the system, and the price is 499 rupees per month for a 10 like a pro account, 10 GB storage. So you can store as much data as possible, but as you go up the storage tiers, the price would increase marginally. And it's available here in the settings section. You can check it out yourself. So someone can work it out and upgrade the plan themselves. These are the prices for different tiers of storage. So we go from 10 GB to 500 GBs currently. And 500 GBs is around 1600 rupees per month. And in that, you get all the features. For the lab-based system, it's a different pricing because that's meant for the diagnostic labs. And if that is what you are trying to ask, like we can discuss that separately after the call. Because there we'll be providing the system, the software, the storage system, which is like a laboratory pack system as well. And a lot of integrations will have to happen with the LIS system, LIS, microscope, scanners, whatever you have. So depending on that, the price will be decided. But again, it's meant for the Indian settings itself.
So I think all of the questions have been answered. Can we wrap it up, Swapnil? If you have anything else to add?
Nothing else from my end. So yeah, a couple of the questions I think what you had shared with me, Dr. Atul, they were around building more capable, like upskilling in the field of pathology. I think someone else. One second. Actually, it's a
Sorry?
personal.
Swapnil, your voice broke. You were asking something like the questions I shared were from the Google form. Are you specifically asking about any particular question?
No, I think I just wanted an understanding of are people looking at building their own AI models or learning about them or deploying them?
I Yes, I think this is a mixed population in the group as well. Some wants to learn how to build their own model, some of which are already my participants, those who are learning the basics of AI modeling itself, while others are like they just want to deploy it in their setting, some ready-made solution. That's why I contacted Dr. Devansh for this particular workshop, so that those who really want to integrate in lab some solution can get to know like how these things work. And so there are some others who just want to try it out, like last message, if you can read in the chat box also, someone wants to integrate it with their for thesis purpose also. So there are mixed this is a mixed community.
So what I was saying is clearance is not required. It's like any other data storage or annotation system, but just like it's cloud based and you can use it much seamlessly. Yeah, sure. It's in the PPT as well. I'll share it here. So I shared my email ID in the chat here. Anyone who has any questions or follow-ups or wants to discuss anything can either reach out to me on WhatsApp or feel free to shoot a mail on the mail ID. I'll put my number here as well, maybe. So there is like, I understand that pathology has been more of a like a manual field where even education in colleges right now is through the microscope modality. So we are trying something here, like, and we have done this with a couple of institutes. We're looking to scale it across the country, building out institution specific digital style libraries for the institution itself. So, like the platform library where you can see slides from across the country, this will be a pool of your own slides, which will be storing in a compressed format. It will be owned by the institute, and only the institute people, instructors, students, all of them will be able to access it. So you can create instructor accounts, student accounts. Students will mostly be looking at it for free itself. And this will be a personalized library for the institute.
So I think that covers all, and we can now wrap it up this session. If there are any other follow-up queries, you can ask in the WhatsApp group, or Swapnil has shared his email ID as well as WhatsApp number also. So you can contact him through that, or the website name is quite easy, Turocrates.ai itself. You can check it out that as well. So thank you so much, Swapnil and Dr. Devansh, for this workshop come hands-on session. And thank you so much all the participants for joining in. I will stop the recording now.